Okay, I think we're ready to go. It is my pleasure to introduce Todd Schwartz, who many of you, if not all of you, know. Todd is a professor both in nursing and biostatistics at UNC. He co-directs our methodology of our CCCR and has been involved with research part of the MCRC and now CCCR for quite a while. Todd is an expert statistician with work in a lot of different areas, including statistical design, analysis, dissemination, and he is also an outstanding educator and has published in innovative pedagogical methods, including the flipped classroom. So Todd is a long time collaborator of many of us at Thurston, and we're glad to hear him talk today about a really important topic to many of us, and that is statistical power and sample size determination.
All right, thank you. Thank you, Kelly. Thank you everyone for joining today, and hopefully this session will be helpful. I'm trying to keep it at a fairly introductory level, but would welcome questions at the end. So here is what I'm hoping we can cover today is make sure everyone gets a sense of what this concept of statistical power is all about. I want to show some basic formulas just to give an intuitive sense of how different pieces are working together and the kind of inputs that are needed. I'm going to talk a little bit about some choices of study design, particularly dealing with randomized clinical trials and what that impact might be on the power. Talk a little bit about how we can actually obtain estimates that go into these calculations. And I do want to give a couple examples from the literature so you can see how this is reported and used. And if we have time, I might be able to show a little bit of some software that's available for sample size and power calculations. So here is a quote from a text on clinical trials. I do want to note that power is not limited to clinical trials, so I don't want to give that impression that it's not relevant in other types of study designs. But this particular quote comes from a clinical trials context, and it says that these trials should have sufficient statistical power to detect differences between groups considered to be of clinical interest. Therefore, calculations of sample size with provision for adequate levels of significance and power is an essential part of planning. And what I've done here is to take these words and highlight in yellow these different pieces that we'll be talking about and seeing how these are related mathematically to get this overall sense, this gist of, again, these inputs and how power is operating. And what I want to note, what I have in red and underlined there to really emphasize it is just a reminder that power is something that is relevant in the planning stages. Okay, so power a lot of times comes to the forefront after a study is complete and after the analysis is done, and perhaps your p-value was not as small as you had hoped, and then you start thinking about power. That is not the time to be thinking about power. Power is a consideration that should be made in the planning stages. So again, just want to lead off with that. So what is power? Why is it important? Well, let's suppose that you are at the stage of developing your research such that you have already specified the questions that are of interest and possibly worked with a statistician to state those in terms of hypotheses so that you have a null and alternative hypothesis. And at that point, you are ready to be addressing this issue of power. And essentially the question that you want to be addressing is, how big does my sample size need to be so that my data collection and my data analysis will be able to address your research questions with a high probability. And when we say it that way, we're basically saying with sufficient power, with a adequate level of statistical power. And one way to define power is what's shown at the bottom of this slide, that power is the probability of observing a statistically significant result in your study. So many times that is our goal, making sure that we are able to achieve statistical significance. And so we want to have a high probability of doing so. Here are two alternative definitions. All three of these are valid definitions, but if one of those kind of speaks to you more clearly than the others, that's fine. So we'll just state it different ways. You can say that power is the probability of rejecting the null, but we're assuming that a specific alternative is true. Okay? And another way to say it is that power is the conditional probability that your study is going to be able to prove your hypothesis, assuming that that hypothesis is actually true. Okay, so here is a visualization of what's happening with statistical power. And this is a slide that when I've given this talk in the past, I tend to spend actually a lot of time on, because if we can see these different aspects, these different inputs, and visualize them here, it's very useful to give that intuitive sense of how power is working, and how if we make tweaks or modifications, or think about how things like variability and significance level, if we are to modify those, how that will have an impact on statistical power. So let's start off by looking at what we have here. You can see that we have these two curves, okay, one with solid line, one with dotted line, and you can see here in the legend it says that the curve with the solid line applies under the null hypothesis. Typically, the null hypothesis is that of no difference, okay, no difference between groups if we're thinking about a two-group kind of comparison. And the alternative here is represented through the dashed line. Okay, so what these curves are, hopefully they look kind of bell-shaped or Gaussian, maybe normally distributed. These are statistical distributions, okay? And one reminder is that although this y-axis is labeled here as the probability of the result, statistical distributions, the height of these curves does not represent the probability. Okay, the probability, the way that these distributions can be used to determine probability, is through area under the curve. Okay, so another way to say that is that if I were to take a valid distribution, if I were to determine the total area under the curve, that total area is going to be 1. Okay, so the entire distribution has a probability of 1. And usually what we do is we partition these distributions, and then we look at the area under the curve either above or below a certain threshold to determine a probability. So for example, one that we commonly use is the significance level, the alpha, the type 1 error. And if you recall the way that that's defined, and I'll have a refresher here in a little bit, is that is the probability of rejecting the null when the null is true. And so if we focus on this null distribution, okay, if you think about what I just said in words, I'm going to focus on this null distribution, okay? When I reject the null, that says I am going to be in the tail of the distribution, away from what I would expect that value to be. So again, if I'm thinking about a difference in means, for example, if there's no difference between the groups, it's going to be centered at 0. As I get more and more extreme in either direction, that gives me evidence against that null. Okay, and what I do when I set my type 1 error rate or my significance level is I say, where is a threshold at which I have, let's say 5%, if I use a type 1 error rate or a significance level of 0.05, okay, 5%, where I have 5% in that tail. Now, often what we do is we have a two-sided significance level, and what that implies is that the 5% are split between the upper and the lower tail. So what that would mean is that I actually would decide where to draw this vertical line so that I have 2.5% in that upper tail. I would have a corresponding 2.5% in the lower tail, but basically I'm going to decide this line is going to be drawn where I have an area under this upper tail that is 2.5%. Okay, so that's my rejection region. Okay, so anything that is to the right of this line is going to lead me to reject that null, to say that I have sufficient evidence to reject that the actual value is 0. Okay, so this is anchored to the shape of this null distribution, again, such that I have 2.5% in this upper tail. Okay, so I do have this alternative distribution. You can see that the null is centered at 0. The alternative, I don't have something down here on the x-axis to show me where that is, but what I am doing is I am taking that distribution and I am shifting it, okay, and the amount by which I shift it is representing this effect size, or what the difference in means that I believe truly applies. Okay, so under the alternative hypothesis that there is a difference, I actually specify what I believe that difference to be, and that alternative distribution is going to be centered at that value. Okay, so again, you can see these distributions have the same shape, and they are just shifted, and the amount by which they're shifted is this effect size. Okay, so it's centered. I have the same shape. You may recall that variability is reflected, okay, in the shape of the distribution. Another way to say that is how fat or how wide this distribution is versus how narrow or how peaked the distribution is. Let me try to maybe draw this, see if I can get something to work here. If I were to represent the same null effect, no difference between groups, okay, a mean of 0, but with more variability, okay, I might get something that looks like this. And I'm not an artist, but I'll try, okay? And basically you can see what I've done is I've tried to draw this wider or fatter type of distribution where those tails get pulled out. Okay, and if you remember, I said the total area under the curve for a valid distribution has to be constrained to be 1. So if that's the case, if it's constrained to be 1, when I pull those tails out, this peak is necessarily going to be pulled down. Okay, I get more of the data or more of that area spread out, that distribution spreads out. Okay, conversely, if I were to try to draw a distribution with less variability, okay, what I'm going to get is something like this, where I'm going to pull those tails in, but I'm going to get a more peaked distribution. Again, I'm not an artist, so just try to imagine this, that basically I'm pulling the tails in, and when I pull them in, I'm going to make a more peaked distribution. So more of that distribution is piled up around that center value. Okay, well, why am I spending so much time on this? Well, what I'm trying to illustrate here is the effect of the variability, the underlying variability is going to have a big impact on power, okay? Now, what is power? How is power represented in this visualization? Well, I have this note here that power is equal to 0.80 or 80%, and there's an arrow pointing somewhere here. Well, where it's pointing, if you remember the definitions that we had in words, we said power is the probability. So again, it's going to be an area under one of these curves. Okay, the probability of rejecting the null. That means I am going to be to the right of this vertical line in the rejection region, assuming that the alternative applies. That means I am under this dotted or dashed line, okay? And so I'm everywhere in this rejection region. So if I were to try to shade this in, let's see if I can do this here and draw this in yellow. Okay, if I were to shade in this entire region, okay, and determine what that area is, that is how power is represented. So in this case, 80% of this distribution, or the area under the curve of the dashed line to the right of the vertical line, that would be 0.8. That's 80% power. Okay, so how does all this relate back to what I was saying about the variability here? Well, if you think about it, what happens is if I have less variability, which is this red curve, okay, what's going to happen is as I pull this tail in, okay, that means that my vertical line where I have 2.5% that's to the right of this, okay, is going to get shifted over to the left, okay? And so I'm going to have a similar narrowing of the distribution under the alternative with this dashed line, and I'm going to get a greater amount of the area under that dashed line that's to the right of this new vertical line. Okay, as I pull the tails in, okay, that vertical line is going to move as well, and I'm going to get greater power. On the other hand, if I think about my this distribution here that's wider, okay, as I have more variability, as the distribution is spread out more and more, okay, this line's going to be over here somewhere, okay? And again, I'm going to have a similar widening of the distribution under the alternative, okay? And when I shade that in, you see that I have less power. I'm going to have a lower probability that's represented through that area under that dashed line, and my power is going to decrease. Okay, so again, I spend some time on this visualization, but the more that we can see how these distributions are working and the impact that they would have on power, I think the more helpful that is, especially as we start looking at the formulas, the math equations that are basically quantifying what's going on here. Now, one other thing that I can mention here is, and maybe it's a little bit easier to see, is this effect size. If so, what I just illustrated was the impact of changing the variability. We can also think about what happens if I change the effect size. Okay, so if I change the effect size, if I make the effect size bigger, okay, what I'm doing is I'm taking those distributions and I'm going to spread them out even more. Well, this line is going to stay the same. I'm going to have a new, okay, I'm going to have a new alternative hypothesis, and I'll exaggerate it here, okay? That's going to follow this same shape, but just be shifted to the right, okay? Well, you can see that if I look at the area that's to the right of this line, this isn't going to change because the shape of the null distribution didn't change, okay? Now I'm going to have a power that's nearly 1 if I shade all this area under this curve, okay? Or if I do it the other way, where I'm interested in detecting a smaller effect size, okay, I'm going to move this distribution, okay, closer to the null, okay? I'm only going to have this amount of area that would be shaded. Okay, and I'm going to have a decreased power. This is why when I'm interested in detecting a smaller effect size, I have lower power to do so. Or conversely, I need more sample size in order to detect that smaller effect. Okay, so just two last comments before we move on. The first is the effect of changing that type 1 error. Okay, so if instead of a 5% significance level, if I wanted to use, let's say, a 0.01 significance level, okay, that means I'm going to move this vertical line, okay, here so that I only have this 1% or 0.5% if it's two-tailed, okay, under that upper tail. So I'd actually move that vertical line so that my rejection region actually moves out more extremely into the tail. Okay, so again, I'm going to have lower power when I have a more stringent type 1 error rate. And then the last thing I want to say before moving on is the effective sample size. So it may or may not be clear how sample size is being illustrated or displayed in this particular figure. Well, it's actually displayed in a very similar manner to what I described for the variability. And that's because this distribution is actually not the distribution of the population that I'm drawing from, that I'm drawing my sample from, but it's actually the distribution of the test statistic. And so it is a function of not only the variability, but also the sample size. So as my sample size goes up, I actually have more precision around my mean. And so I'm going to have that net effect of a bigger sample size is going to give me that narrower and more peaked distribution. And a smaller sample size is going to give me that wider or fatter distribution. Okay, so I get more precision and a more narrow distribution with more sample size. So what I illustrated originally in terms of the variability would have those same principles applying. Okay, so why is it important? Well, hopefully it's becoming pretty obvious, but we want to have enough power to be able to determine and claim statistical significance when we're testing these hypotheses. Okay, so most people think about power in terms of saying we have enough sample size. People don't always appreciate that it also helps us to not have too large of a sample size. So in other words, it gives us kind of that sweet spot where we have a big enough sample size, but we don't have too big of a sample size. And why wouldn't we want to have a larger than necessary sample size? Well, a lot of times when we're collecting data, it's expensive. It takes resources, it creates work, and there are ethical considerations involved as well. So power is helpful because it gives us, it puts us in that right ballpark, and it keeps us in that sweet spot where it's enough, but not too much. So let's start to formalize this a little bit, and we're going to kind of follow along the lines of what I was describing when we were looking at that figure, and that is to consider the scenario where we have two groups, and we want to compare those groups and show that one is superior to the other. And by that, I mean to show that one has a larger mean than the other. And so if I want to formalize these in terms of statistical hypotheses, I'm going to specify a null hypothesis where I have no difference between the groups, such that the difference in means is 0, versus an alternative of a difference where that difference in means is equal to some specified amount. This is the effect size that we had in that plot that's showing you how those distributions are shifted. So the effect size that I had laid out in that plot would be this amount delta. It's different from 0, and it is a specified amount. I need to say, is that 1 unit? Is that 10 units? Is that 20 units? What is the amount? What is the effect by which I expect that shift to occur? Okay, alternatively, if I don't have a continuous variable that can be represented through the mean, I might instead have a dichotomous, okay, or binary outcome variable that I'm interested in characterizing through the proportion, and that's what the pi's would be. So again, I can specify this in terms of a difference in proportions. The null is that there's no difference. Those proportions are the same, so the difference is 0. Or I can specify an alternative where the difference is a set amount. Is it 10 percentage points? Is it 25 percentage points? I can specify it this way, or I might specify it in terms of a relative risk or an odds ratio. Well, what are the pieces that come into play? And these are the pieces that we talked through as we looked at that figure, but we can state them here. There are 5 main considerations. There is the sample size. And what I have in parentheses here is the important consideration. Am I going to assume that they are the same in both groups, or do they differ? That's going to have an impact on power. Okay, my significance level. and we talked about the difference between whether it's one-sided or two-sided. If it's two-sided, I'm splitting it in the two tails. Okay. The third is the power, and I have that represented here as 1 minus beta. So my significance level is alpha, which is my type 1 error. Beta is my type 2 error. And again, I'll have a little refresher on that, I think, on the next slide. 1 minus beta is my power. Okay, delta is that difference that we want to detect under the alternative. And sigma is my standard deviation, or my measure of variability. Again, how narrow or wide is that distribution? And again, a consideration, am I willing to assume that I have the same amount of variability in both groups or not? And that determines which method I'm going to use. Now, I do have a note here that we have to be careful, because we can have two different people talking about effect size, and they're using the same words, but they mean two different things. So sometimes people talk about the effect size and they talk about the difference in means. Other times they talk about effect size and they're actually standardizing the effect size, so that rather than delta alone, they're actually focused on the ratio of delta to sigma. Okay, and the way that you can tell is if it's expressed as, say, half a standard deviation difference, or 2/3 of a standard deviation, or a fifth of a standard deviation. If they're using an effect in those terms, okay, they're talking about this ratio. And we'll see when we look at the mathematical formula why they might be doing something like that. So essentially what we can do is we can write a formula, an equation that relates these 5 quantities. And then algebraically, we can manipulate that so that if you specify any 4, we can solve for the 5th. Okay, so theoretically, we could specify any 4 of these and solve for the 5th. We typically don't solve for things like the significance level. Okay, we would set that a priori, but theoretically, we could do that. I have a 6th step on this slide because it is a separate step. I would call this like a 2-stage or a 2-step kind of process, where I can determine, for example, the sample size under the specification of 2 through 5. And I can say that's the sample size that I need. What step 6 does is to say, after I've determined that, I can say, what sample size do I actually need to target, so that after I have any dropout or loss to follow-up or attrition, what is that dropout? What would that effect be to allow me to get back to the sample size that I need? Okay, so another way to say that is, if I expect to have, say, 20% or 25% attrition, I need to take the sample size that I've calculated and inflate that, so that after the attrition, I end up with the calculated sample size. Okay, so there's just another step in the process to provide that inflation. And we'll come back to that when we look at the example. So here's that refresher on type 1 and type 2 errors. Again, alpha is my type 1 error, beta is my type 2 error, and that's important here because power is 1 minus beta. Okay, as a reminder, we can either have the true state that's unknown, okay, that we're interested in and we want to have some evidence for or against. If the null is actually true, that these two groups do not differ, okay? If my decision based on the data is not to reject the null, then that is no error. But if I do reject the null, then I've committed a type 1 error, and the probability of that is set at alpha. Okay, that's where I'm going to draw that vertical line, okay, and create that rejection region. On the other hand, if the alternative is correct and I don't reject, then I've committed that type 2 error, the beta. Okay, where I want to be is in this cell, so that the alternative is correct and I've rejected the null. Okay, that's shading in that part of the curve that's to the right of the rejection region, okay, or in that rejection region, and that is my 1 minus beta, that's my power. So the significance level is the probability of rejecting the null when the null is true. Power is the probability of rejecting the null when the alternative is true. Ideally, I have a small alpha and a large power. And the way that I can make power larger is by increasing the sample size. Okay, also I want to note that power is a function of the specific alternative hypothesis. My point here is you can't just give a general alternative hypothesis and say there's a difference between the groups. You actually have to specify what that difference is. Again, you need to say what is the effect so that I know how far apart those distributions are. So the power is going to vary with different values of delta. Okay, I'm going to get one value of power when delta is 1. I'm going to get another value when it's 1.5, another value when it's 2, and so on. So typically, what do? Well, typically we specify our significance level, our difference, and the variability, and we either compute the sample size for a specified level of power, typically something like 80%, 85%, 90%, or if we have a fixed sample size, we might say this is the power that that sample size will provide for us. Okay, one variation on this is sometimes for a pilot study where we know that we are not well powered and we don't expect to be well powered. What we might do instead is to say for this sample size that we're using for the pilot, in order to get 80% power, we would need to see an effect size that's a certain magnitude. Again, not expecting to see that because that's not the function of a pilot. But that's one way to show reviewers that we're aware of the issues of power and sample size, and to say in the event that the effect is this big, we would be powered in the pilot. All right, so let's actually look at one of these formulas. And this is probably one of the simplest sample size formulas that we have, okay? And what you can see is that I have these 5 quantities. This is actually expressed and I've algebraically solved it for the sample size. So I have sample size n on the left. You can see I have my type 1 error. I have my type 2 error. I have my effect size delta, and I have this standard deviation sigma. I didn't say power, but if you remember, power is 1 minus beta, the type 2 error. So power is actually represented through the beta here. And what you want to note is that I have, it's not a straightforward equation in the sense that it's not linear. You have this reciprocal relationship with the square of that difference. I have not just sigma, but I have sigma squared, the variance represented here. And the way that the alpha and beta come into play is not directly, but it's through their corresponding z-score. Okay, so the z-score is from the standard normal distribution, distribution with 0 mean, variance 1, where I'm essentially saying what is the value of z that would give me, in this case, alpha to the right of that, or in this case, beta to the right of that. So, and actually, a lot of times what we use for z is alpha over 2 if it's two-sided. So if, for example, I had a two-sided 0.05 significance level, okay, the z that would correspond would be 1.96. So 1.96 would be this term here. If I had 80% power, the z that corresponds to having 20% above that is 0.84. So if I had a two-sided 0.05 and 80% power, this piece here would be 1.96 plus 84. And that's what I would have in parentheses for the purposes of this sample size calculation. Okay, what I want to show you is that I'm just repeating that formula here. And I want to note that actually, if I don't have sigma and delta separately, I can express this in terms of their ratio. Okay, so this is that standardized ratio or that standardized effect size that I showed you earlier, that for the purposes of this formula, I don't need those values separately. I only need their ratio. So again, the fact that maybe I'm interested in detecting half a standard deviation, okay, you don't need to tell me delta and sigma separately. You just need to plug in 0.5 into this form of the formula. Okay. Also, if I do some algebra, I can re-express that in terms of power. Again, the piece that I want to focus on is the z sub beta. Okay, it's a little bit more complicated because I need to use that standard normal and the area under the curve for a standard normal distribution. That's what this phi function is, but I can do that. Here is the counterpart to that if I have a difference in proportions. Okay, and you can see that this piece looks the same and this piece looks the same. What's different here is the piece involving the variances, and that's because I have a relationship in a binomial distribution between the proportion and the variance. Okay, and that's important because the implication of showing the formula in this way is that when I have proportions, I can't just specify the difference. Okay, the difference, that's all I need here for the denominator. But up here in the numerator, I actually need to specify pi1 and pi2, okay, the proportion in each of those groups. And that's important because let's say I'm interested in a 10 percentage point difference. Well, I might have 0.2 minus 0.1, or I might have 0.5 minus 0.4, okay? And both of those will give me 0.1 squared in the denominator, but those scenarios are going to give me different amounts in the square brackets here. So I need to actually specify what those proportions are when I'm dealing with proportions. Okay, so what are the implications? What can I take away from those formulas if I don't actually want to do the math? Well, first of all, sample size and power are directly related. Okay, as one goes up, so will the other. In order to get more power, I need more sample size. Okay, so sample size can be thought of as your currency so that you can buy more power. And so this is really emphasizing the importance of those participants. Okay, so we want to make sure that we are treating them as a valuable commodity. We want to minimize loss to follow-up, minimize missing data. Okay, and again, if I put this into words, this slide just sort of demonstrates how these different quantities are related. Again, it's consistent either looking from the formula or looking from that figure that we went through previously. Here is an example of a power curve. Okay, this makes the point that as we get different values, so when I do any one calculation, I'd get 1 point on this curve. But this is a power curve where I'm actually fixing the significance level, the delta, and the sigma. And then I'm going to plot power as a function of sample size. Okay, so you can see, again, as I mentioned, that as I increase my sample size, I'm going to increase my power. However, you can see that it is not in linear fashion, right? I have a more complicated type of relationship here. And this is important because I do have this monotone increasing kind of function, but where I am on the curve is going to be informative to me. What do I mean by that? Well, if it turns out that I'm somewhere up here, okay, on this plateau, okay, the fact that this slope is nearly 0 is important because it says that if, for example, I have about 30, but something happens and I'm only able to collect data from 28, okay, the fact that this slope is so flat, if I go down to 28, okay, my vertical loss is very small. My hit on power is going to be very small. Likewise, if I have 30 and I came across more resources and I was considering adding a couple more, okay, my increase in power would be very small. That's in contrast to if I'm over here on the steeper part of this power curve, where any change either to the left or right, meaning losing or adding participants, sample size, is going to actually create a large vertical difference, either a loss in power or a gain in power. Okay, so if I understand where I am on the power curve, that can be informative to me in terms of how I'm recruiting and so on. Okay, so I've done a lot of talking. Let's see how some of this is actually communicated. This is a New England Journal of Medicine article. The topic of the article is not as relevant to the group unless possibly you have small children and you're dealing with ear infections and that sort of thing. But the purpose of me picking this is because in their methods section, they have these two sentences where they describe their sample size determination. And so what we can see here is they say, we estimated that with 260 patients, the study would have 90% power to detect an absolute reduction of 15 percentage points in the rate of treatment failure in our intervention group as compared with the placebo group, assuming a 25% rate of treatment failure in the placebo group with a type 1 error of 0.05. Okay, second sentence, we plan to enroll 320 patients to account for a possible 20% rate of withdrawal from the study. Okay, so what they've done is this first sentence talks about kind of those first 5 considerations. And then the second sentence talks about that inflation, that 6th step, so that after withdrawal, okay, possibly 20% withdrawal, then I'm going to go for my 320 and end up with my 260. Okay, but you can see just in 2 sentences, they've described their justification. And if we went through this, we can see they have their sample size, they have their power. Here they have that difference in proportion. So the difference in proportions would be 0.15. And we made the point that it's not sufficient to just give the difference. They actually need to specify it. So they give this additional context that they're assuming 0.25 in the placebo group, okay, and that's treatment failure. So we can infer that in the intervention group, okay, they're going to have a lower treatment failure rate. So that would be 0.10. So their difference of 0.15 would be 0.25 minus 0.10. That's what would go into that sample size formula. And then they say they have a type 1 error rate of 0.05. What they don't say is whether it's one-sided or two-sided, but the strong convention is that that would be two-sided. So again, here's an example of how that might be reported. So let's just talk quickly about the impact of your choice of study design on your sample size. And what I want to compare is kind of your typical individual level randomization with either a stratified random assignment or a clustered randomization. Okay, if we think about a stratified randomization, typically the reason that we want to do stratification is because we might have strata that are more homogeneous within a stratum. And essentially what that does is that homogeneity is going to help me reduce the variability. So hopefully I'm able to have a lower standard deviation. And what that can do is that can help increase the power. That's going to make those distributions more peaked. Okay. On the other hand, I can have clustered randomization, where I'm actually, instead of randomizing individuals, I'm taking groups of individuals, I'm randomizing the entire group, but I'm measuring at the individual level. Okay. Well, the problem there is I actually get the opposite, where I actually have less efficiency. And that can be captured through what's called the design effect. And the design effect can be written in this way, where I have 1 plus the ICC, which is the interclass correlation, okay, and that is times the average size of the cluster minus 1. Okay, so the size of the clustering, if I'm randomizing clusters of 10 patients or 15 patients or 4 patients, okay, that's going to come into this as well. What I'm going to do is I'm going to multiply that design effect by the variance in my sample size formula. And so the impact is through that design effect. So for example, if I have an interclass correlation of 0.05, an average cluster size of 10, if I plug that in here, I get a design effect of nearly 1.5. What that means is that I'm inflating the variance piece of that sample size formula by about 50%. Okay, so that's a big impact through using the cluster randomized type of design. So that's important to know. So a few practical considerations. A lot of times these calculations can't be done in a vacuum. Okay, I can do the math, I can tell you what the sample size needs to be, but that can be unrealistic given either logistics or budget constraints and so on. And so there needs to be kind of thinking about it from that practical point of view as well. Sometimes we're in a situation where we have difficulty accessing individuals who would be eligible for the study, or maybe you're dealing with a rare disease. And so it's important to note that as well, that I can come up with a number mathematically, but again, it's not realistic to actually recruit that many. A lot of times we don't know exactly what these values might be. We don't have exact values for, say, the variability or for what that effect size would be. So in that case, doing some kind of sensitivity analysis to say, well, we think the standard deviation is going to be about this value, but let's also look at what the power would be if it's a little bit bigger or a little bit smaller. Okay, so that kind of sensitivity analysis can be helpful. A lot of times when we are designing studies, we're not just measuring one outcome. We can have multiple outcomes. One way to address that is to specify one as the primary outcome and to focus our power calculation on that and determine sample size based on the primary outcome. Sometimes that's not possible. We might have a list of primary outcomes or outcomes that we're interested in which case we might want to calculate power or sample size for all of those and then choose the largest to meet that most stringent requirement so that we know that all the other ones will be well powered as well. Here's a slide that just gives some recommendations if we don't have good information on these various inputs or components that might go into that sample size formula. So we might want to power based on a minimum meaningful difference or a minimal clinically significant difference and determine, what is the amount by which people would actually change the way that they practice, or what do they consider to be important, and we could power it that way. We can, of course, refer back to similar previous studies through a literature review. If we have the money and the time, we can actually conduct a pilot study to generate those estimates. So again, the pilot study is not expected to be well powered, but we can gain information that we could use for the sample size calculation for the well-powered study. Sometimes there are some rules of thumb. If we don't have good data for the standard deviation, maybe we have some other information about variability that we can use to generate kind of a rough estimate. Sometimes you see, again, if I use this capital delta as the standardized effect size, the number of standard deviations, there are different rules of thumb that are used for that. So for example, half a standard deviation might be considered a moderate effect, and I might power it for that. And again, it's important to get this uncertainty accounted for possibly through a sensitivity analysis. In terms of this ethical kind of consideration, just coming back to that, if my sample size is too small and my study is underpowered, such that I have a small chance of actually showing statistical significance, that can be considered to be unethical when I have a little chance to actually show that treatment to have benefit. On the other hand, if my sample size is too big, that can be an ethical issue because I've exposed so many individuals to an unproven treatment when I could have done so with a smaller sample. So again, those ethical considerations are something that you want to keep in mind. Thinking about how to interpret power, okay? So a lot of times what we say is that this study has 85% power to detect a true difference of a certain amount between treatment groups. Just because you achieve that sample size does not guarantee, right? It's a probability. It's 80%, it's not 100%. Also, if you don't achieve the target sample size, it doesn't mean you won't show statistical significance, okay? And then the last point here is that sometimes we're in this situation where we have a really, really big sample size, okay, that we can end up with really tiny p-values that correspond to differences that don't really mean much. Okay, so it's just this reminder that we need to balance statistical significance with clinical or practical significance. All right, last thing I want to cover here is just to mention, I do not typically go around and do those sample size formulas on my napkin at lunch, although you might think of statisticians as enjoying that. We have nice software that will do these kinds of things for us, and you can see some of those listed here. I'm going to focus on the first one, which is nQuery. And the reason that I want to focus on that here is, first of all, that is available to us here at UNC. And we can either install that locally on our computer, or we can access that through the virtual lab. So if you go to virtual lab, all one word, .unc.edu, and you log in with your Onion, nQuery is one of the software packages that you can run through the virtual lab. I recommend it because it has a very user-friendly kind of interface. It's very easy to input these parameters. You don't need code like R syntax or to figure out SAS proc power to figure out exactly how to specify this information. So let me show you another example from the literature and then show how that can be used in nQuery. This is actually a recent JAMA publication, and this is a little bit more relevant to this audience, hopefully, than the ear infection example. This is looking at a randomized clinical trial in ankle OA. And what I wanted to pull here was there was this little section in the methods where they talk about their sample size justification. Okay, and what we can see here is they say the study was designed to have statistical power to detect an MCID, a minimal clinically important difference, okay, the smallest clinically important difference, and they determined that to be 12 points on their primary outcome of this score, and you can see what that stands for up here. Which is, I think it's expressed as a percentage. It goes from 0 to 100. They talk a little bit about the justification. Okay, so again, for maybe how they came up with that value or sort of putting it in context. They put it in context in terms of knee and hip OA, and they basically justify it that way. Okay, because there's not necessarily a right answer to what that is. Okay, but they're defining it to be 12 percentage points. And then in this sentence, what they say is with a two-sided significance level of 5% or 0.05, under 90% power, a dropout rate of 10%, that's that sixth step, okay, an expected standard deviation, sigma, of 16.3 percentage points, okay, they're saying that that leads to a sample size calculation of 50 patients per group, which would be 100 in total. So they're assuming the same sample size or balanced allocation. Okay, so again, they have just these few sentences. They provide their assumptions. They give some context, and it's really this last sentence here where they kind of provide that information. Well, here is a screenshot from nQuery. Okay, and essentially what you can see here is that it is like a spreadsheet format. What I've cut off is that there are actually like 20 columns that it allows you to specify each column as one scenario for which you're calculating power or sample size. Okay, so what's nice about that is if you think back to that sensitivity kind of approach, is I can have a side-by-side comparison. If I want to think about a slightly bigger standard deviation or slightly smaller, or if I'm not sure about that effect size, I can tweak that and then basically see the bottom line, how that affects either my sample size or my power. Okay, but it tells me what I need to input, and then I just have like these cells like in a spreadsheet that I can put in the values. It has a lot of other features, like it will provide a scientific article reference. It can actually create a sentence where it puts together the information that you can use as a starting point to drop into your methods section or into your grant proposal. So it's a very user friendly type of software for this. But in this particular example, what I've done is just to try to replicate what they reported in that JAMA article, the two-sided 0.05 significance level. Okay, my MCID of 12 percentage points with a standard deviation of 16.3. Okay, it will calculate that standardized effect size for me. You can see that's about 3/4 of a standard deviation. Okay, so this is the standardized effect size of 0.736. And for 90% power, okay, this is actually saying I would need 40 per group. And what they reported is 50 per group, but they said that that was accounting for 10% dropout. I would actually say that looks more like 20% dropout to me, to basically get you from a 50 per group down to 40 per group. But this kind of allows me to replicate their calculation. And again, it shows how this software can be used. So with that, I will stop. I know I'm almost at time, but just acknowledging some of the previous iterations and some of the people that have contributed to this. And I know we don't have much time, but I'm happy to take questions that you might have.
Thank you, Todd. That was wonderful, as usual, very clear and comprehensive. Any questions? So I'll read this question. When calculating the, oh, let me pull up the full thing. When calculating the power sample size, I wondered if it is needed to use the same instrument. Let's say I found the similar research about fatigue, but how they measured fatigue is using a different instrument from the one I'm using. Can I still use their estimate, their results to estimate power and sample size?
Yeah, so that's a good question. You know, I've mentioned sort of this use of doing a literature review to maybe figure out, you know, what should my effect size be, or what should my variability be. Of course, if you are going to switch up instruments, or you're going to change study populations or things like that, you're not necessarily going to have apples to apples. So, for example, if you have fatigue and you're going to switch instruments, you're going to use something different, you're going to have to be very careful, because probably those effect sizes are not going to translate, your variability is not going to translate. However, this is another place where using that ratio of the effect size to the standard deviation could be valuable. So you could argue that the standard deviations, when you do that delta divided by standard deviation calculation, you're making this unit free. Okay, so you might use that as an argument to say, I'm going to translate. In this study, they used this instrument and they saw 1/3 of a standard deviation change. Okay, in my study, I'm going to use this other instrument, but I'm proposing that on a standard deviation unit basis, okay, I'm expecting a similar change, a similar magnitude of change. So I would caution against using the actual values, especially if they're on completely different scales. But when you standardize it to the standard deviation, that might be a justification to say I'm expecting to see a similar magnitude that way.
All right, great. Well, we are about at time, so I think we will end here, but there may be other questions. Feel free to reach out to us, and you should see the poll pop up. If you don't mind, please fill that out before you go. And thank you again, Todd, and thanks for everybody for attending. We appreciate it.
Yep. Thank you, everyone.
Thanks, Todd.
Sorry I'm so long-winded. Take care, everyone.
Great.
All good. Thank you.